by my clock, it is 11 a.m. Mountain Time, and that means it is time for us to get going. So I will kick us off with a big good morning, good afternoon. I know we have people in lots of different time zones represented, so maybe it's morning for you, maybe it's afternoon, I don't know, but either way, we are so happy you're here. Hello, everybody. My name is Talia. I'm part of the Virtual Experiences team here at the Denver Museum of Nature and Science. And I am connected today to two incredible experts who have a lot of amazing science to share with you today. Dr. Stephen Bongiorno from NASA and Dr. Sarah Lipsey from Ball Aerospace. I'm going to add their video feeds in real fast so that they can give you a quick wave. You can see what's going on with them. In just a few minutes, I will pass the proverbial mic over to those experts and let them tell you all about what they have been working on and what the big deal about IXPE is. But I do have just a couple of quick housekeeping items before we get going. Number one, I would like to begin today by respectfully acknowledging that the Denver Museum of Nature and Science is on the traditional lands of the Cheyenne, Ute, Arapaho, and Oceti-Sakowin nations, as well as other traditional keepers. Indigenous knowledge has stewarded and governed land since time immemorial and continues to feed scientific knowledge, and it's important to us that we call that out. I also want to acknowledge that we are currently connected to students from all across the United States. I actually need to look at my list to make sure I get everybody on there. So a big hello to students from Colorado, Michigan, Indiana, Arizona, and Alaska. So we've got lots of students on with us today. We are so excited and grateful that you've chosen to spend some time with us today, and we hope you're ready to learn something cool. If you are one of our on-camera schools today, please stay muted until we call on you. I will let you know when it is your turn to ask a question, and when that time comes, we will handle unmuting your microphone, or you might need to do that on your end, and as well bringing in your video feed so that we can all see your smiling face. If you are one of our off-camera participants today, that means we can't see you or hear you, but you can still participate with interactive polls. You can type questions in the chat, and I know we have a couple of questions that we will ask you to reflect on today. So still lots of ways to interact with us, and we'll be excited to hear your questions and, of course, your responses to our questions, too. Without any further ado, I'm going to vote that we go ahead and get started. So first, we are going to hear from Dr. Stephen Bongiorno from NASA. He's going to tell us a little bit about the IXPE mission and about what about IXPE will study and some of the science a little bit behind it. And then Dr. Sarah Lipsey from Ball is going to tell us a little bit more about something exciting that she has going on behind her. So we'll check that out in just a few minutes. For now, it is my distinct pleasure to introduce Dr. Stephen Bongiorno. We'll bring him up on the video, and we will have me disappear from the screen in just a moment. So Stephen, take it away.
Okay, hi everybody. I'm really excited to talk to you about IXPE. So first I wanted to say IXPE stands for the Imaging X-ray Polarimetry Explorer. So this is a space telescope that's going to launch later this year, and it's going to study some of the most extreme objects in the universe. Stuff like black holes, neutron stars, and other objects that are easier to see when your telescope can see in X-rays. So to get a little bit more specific, IXPE will be able to make images of the X-rays emitted by these objects and also measure the polarization of those X-rays. Could we see an image of the telescope right now? Maybe the image of it flying in space?
We will have that up for you momentarily. Right now, we're looking at a black hole with some ejecta. So we'll have that up for you in just a moment. There's our telescope in space. Artist rendition.
So that's an artist rendition of IXPE, what it will look like when it's making observations in space. So I was saying that IXPE is unique because it's going to make images of X-rays and also measure the polarization of those X-rays. Polarization is the direction that the X-rays are oscillating, and oscillating means to go up and down. So you might have heard of X-rays before, but before we keep going, I wanted to hear from you guys about why you think X-rays are important. Can we put up the quiz slide?
Yes, we've got that quiz slide up, and we'll see a poll question popping up in just a moment. Would you like to introduce that one?
Sure, I can read through the quiz. So why do you think X-rays are useful? X-rays can be used to see inside our bodies. X-rays can show us where some objects are in space. X-rays can tell us some properties of objects in space, or all of the above.
All right, so teachers, go ahead and survey your students. If you're learning together in a big group, you can let us know maybe what majority rules. And if you are a remote learner, you can just cast your own vote. Super exciting. You don't have to vote with anybody else. So you're telling us what you think about why X-rays are useful. Why are we talking about them today? What's the big deal about X-rays? So we will leave this open for maybe another 30 seconds or so. We're watching to see the percentage of people that have participated. Let's take a look at those results. If you were not able to respond to the poll, you can tell us what you thought in the chat. All right, it looks like we did have a couple of votes for X-rays are useful for seeing inside of our bodies. Most of our participants said all of the above. So what do you think? Did they nail it?
Very good. That's right. It's all of the above. So you're probably most familiar with X-rays as something that a doctor uses to see inside our bodies. Can we see that picture? There we go. Thank you. That's what a doctor's X-ray would look like. I think that's probably a wrist. So this works because X-rays can go through our skin and muscles fairly easily, but they don't go through our bones as easily, so we can see the difference between the two. Amazingly, X-rays are also useful for helping us figure out what's going on in outer space. So I wanted to go into a little more detail here. X-rays are a kind of electromagnetic wave. I'm sure you've all seen waves of water in a pond. Could we see an image of the water droplet in a pond? Great. So in a wave of water, the surface of the water goes up and down as the wave moves. In an electromagnetic wave, like the name says, it's a wave of electric and magnetic fields that are going up and down. They go up and down and they move through space forever until they hit something. Could we see that picture of the electromagnetic wave moving through space?
We'll have it for you in just a moment, coming up on the screen. Here we go, and it'll play.
Oh, wow, look at that. So the green there is either either the electric field or the magnetic field, and the yellow is the other one. They're at 90 degrees to one another. There it is, moving through space. So the light that we see with our eyes is one type of electromagnetic wave, and so are the radio waves that we use to transmit data over Wi-Fi, or the microwaves that we can use to cook food in our kitchens, or the UV waves that make our skin get tan when we sit out in the sun, and also those X-rays that we talked about doctors using to look at our bones if we get hurt or we need to check if something's broken. They're all electromagnetic waves. So the difference between those kind of waves is that the electric and magnetic fields that make them up oscillate at different speeds. The electric and magnetic fields in an X-ray oscillate much faster than for visible light or for radio waves. And what that means is that it takes more energy to produce them. When we're looking at X-rays in space, we find them coming from things that are very, very hot, like I'm talking millions of degrees, or in situations where, say, the part of a star is being accelerated to almost the speed of light. Those kinds of things emit X-rays. These are the kinds of places where high-frequency waves like X-rays can be created, and these places are often found on extreme objects like exploded stars or black holes. It's important to study these objects in space because we can't actually create conditions like that here on Earth. So it's like, we call it an astrophysical laboratory. We use those objects to study the physics that's happening at these extreme conditions. So just like X-ray astronomy missions in the past, IXPE will take pictures of parts of the sky and measure the positions, the frequencies, the arrival times of the X-rays from those objects that it sees. But unlike other X-ray telescopes that have flown in space, IXPE will also measure the polarization of those X-rays. So like I was saying before, polarization is the direction that the electric and magnetic field oscillate. And knowing the X-ray polarization tells us new information about how those X-rays are made, especially from extreme sources like neutron stars and black holes. Can we bring up that image of the black hole again?
Coming up in just a moment. There it is.
Beautiful. So this is
an
artist.
I will call out, sorry to interrupt you real fast. If you are not able to see the image, make sure you are in gallery view. I do have it set on my side so that most of you should be. If you're on a tablet, you might need to swipe if you're in a Zoom app between different views. If you're in a browser, you might need to toggle your settings just a little bit. Sorry about that, Stephen. Continue.
So scientists already know that objects like this, like black holes, emit X-rays, but so far, no X-ray telescope's vision is sharp enough to tell us exactly where the X-rays are coming from in an object like this. So this picture was made by an artist. We don't know, are the X-rays coming from the light and fluffy corona that surrounds the black hole, or the swirling accretion disk of the matter that's spiraling into the black hole, or maybe it's the jet of material, those jets that are coming out from the poles of the black hole? That's a question that no X-ray telescope has been able to answer so far, and the polarization measurements that we'll make with IXPE are going to help us find out. Fantastic. So that was the end of what I was going to say.
Awesome. Well, one thing I do want to call out here, is just that IXPE is filling a hole in scientific knowledge. I think sometimes we've had a few questions already today about just like, why are you studying this? Why is this important for us to be thinking about? And I do just want to call out what Dr. Bongiorno said of this is a hole in our scientific knowledge. No other telescope has been able to figure out some of the things that IXPE is able to figure out. So that's one of the big points of this mission. We're going to turn it over now to Dr. Sarah Lipsey. I'm going to add her video feed onto the screen. Sarah's going to tell us a little bit about IXPE itself and what's going to happen here in just a little bit when it launches up into space, how it was made, and of course, she's got something going on very exciting behind her. So Sarah, do you want to tell us what you're standing in front of right now?
Yeah, thanks, Talia, and thanks, Stephen. That was a great science introduction. So I'm coming to you today from the IXPE control room at Ball Aerospace facility here in Boulder, Colorado. And I'm in the control room where all the computers to operate the observatory are. But behind this window right here, that is the IXPE Observatory. It's about the same size as me, 5 to 6 feet tall. And the spacecraft is on the bottom. There's an observatory tucked inside there. The black things that you see in the front, those are solar panels, very similar to what you would have on your house or maybe your school. And the white is called MLI, multi-layer insulation. And I'll just pause here and say, scientists, NASA, we love our acronyms. So you'll hear us say a lot of them today. And if we say one and we don't tell you what it is, please call us out. So multi-layer insulation, that's the white sort of blankets that go all the way around the IXPE Observatory. They help keep IXPE cool. You can see they're white, so they radiate. But they also protect from any space debris that IXPE may encounter when it's in orbit. So IXPE is designed specifically to fill that knowledge gap that Stephen and Talia were just speaking of. It only does the particular science case. It only measures X-rays, and in particular, it measures the polarization of them. And we here at Ball, along with partners all over the world, and with our NASA partners, have spent a lot of time designing the IXPE mission to do the science case that it needs to do and to survive the rigors of space. We have a lot of experience here at Ball and amongst our partners and NASA designing space hardware that will launch successfully and then operate on orbit. So at Ball, we built the spacecraft bus, which is the bottom kind of portion of the observatory, and it's very similar to your school bus. It transports the observatory to space. It does not, in IXPE's case, have any propulsion in it. We're going to rely on the launch to get us to the right orbit. But it does provide the power and the data transmission, the thermal control. You might think of a school bus's thermal control as the roof that keeps the rain or the snow off of you. And so it provides all of these control situations for the observatory, for the payload that will measure those crazy X-rays. Once IXPE is on orbit, it needs to get pretty big. To do the science case that IXPE is designed to do, the detectors and the telescope need to be separated by around about 4 meters, 12 feet. And so, but to fit in the launch capsule, the observatory needs to be around about the size of a phone booth. And so that's what you're seeing now, phone booth size IXPE. But once IXPE launches and is successfully on orbit, a special command will be sent and a boom will pop open. And so Talia, if you could play that video of the boom being tested, this is the same clean room space that IXPE is in right now. And you can see the little boom spiraling up very slowly. It goes around 360 degrees 3 times before it's fully extended. And it goes nice and slow with dampers controlling it all the way up, so that none of the really sensitive hardware is damaged during this expansion of the boom. And so once it's on orbit and has this extended boom, we'll start taking the science data and collecting those X-rays and starting to understand the physics that Stephen has been talking about. To survive the rigors of space, we have tested the IXPE spacecraft very, very carefully and diligently. It's been through vibration to make sure that it's going to survive the shaking that it will see during launch. Thank you. We've surrounded it with massive speakers and played really loud rock music at the little observatory to make sure that it survives the acoustic environment of launch. And then we've also done things like putting it in a special chamber to test the electromagnetic interference, the EMI, that the observatory gives off, and also to test that it will not interfere with other observatories on orbit, other spacecraft on orbit. And finally, my favorite test is thermal vacuum. This is where we put IXPE, extend it out with the big boom, into a special chamber that we can suck all the air out of, and then make the chamber get really hot and really cold, just like it will have happen on orbit, to practice that the thermal control of the observatory works and that the whole observatory will survive those giant temperature changes that it will see. One of the most important things about building IXPE in a clean room is keeping it clean. And to help me demonstrate that, I'm going to ask one of my colleagues who's in the clean room to come over and show us his suit. Bunny, could you come over to the window? So this is one of my colleagues who's starting to think about packing up IXPE because it's going to ship here very soon. And I want to show you that he is in a full suit. We call this a bunny suit because it kind of looks like a Halloween costume that you might dress up in for being a bunny, but without the ears and tail. And so what you see is he's full head to toe covered, and you can't even tell, but he's wearing special boots too that help keep his shoes from touching the floor. The only thing you see are his eyes, but he has full gloves on. He's very tactile. He can do anything he needs to do in there, but at the same time keep the observatory incredibly clean. We don't want any hair or oil getting on any of the sensitive components. So before I give it back to Talia, I want to put a question out to all of you in the chat. I'm going to talk after the question break about the orbit and how we're going to get there. And the orbit we're headed to is called a LEO orbit, L-E-O. This is a NASA acronym. And I want to know what you guys think LEO orbit stands for. So I'll break there and hand it back to you, Talia.
Let me put my video feedback up on the screen real fast, and then we will take some questions. I'm also going to bring Dr. Stephen Bongiorno back onto the screen so that we can all kind of be on here together. We'll kind of be a panel while we're answering some of those questions. If you are one of our on-camera groups, we're going to go in a specific order to take questions from you, and I will handle bringing up your video feed, like I mentioned at the beginning, so that everybody can see you. I'll let you know when your turn comes. We may need you to unmute on your side so that we can hear you. And of course, students, tell us your name when you ask your question. We also will pull some questions from the chat. I see that Dr. Bongiorno is going through and answering some of them already, which is great. That means your question will most likely get answered today. Sometimes we get so many we can't possibly answer them all, but we'll pull some to answer live too. All right, and yes, some of you are not able to unmute today. I do see a question in the chat about that. We do have a small group of on-camera panelists today, and others are view-only groups. So you will be able, you're watching from the comfort of wherever you are today, and you can submit your questions in the chat. And of course, like Dr. Lipsy asked, make sure you submit those guesses for what you think LEO stands for, and we'll review in just a few minutes. All right, today we are going to start with, let's start with one question from Samantha Bond's group from Crest Academy, one question from Ms. Bass O'Brien's group from Crest Academy. Both of those are down in Salida, Colorado, so southern part of our state. And then after that, we'll take one question from Advanced Technology Academy in Dearborn, Michigan. And we'll see, I have to look at my paper to make sure I keep track of everybody. After that, we will see how much time we have. We'll pull some from the chat, and we may come back to some of our on-camera schools for more. All right, so we're going to start with Ms. Bond's group. I see you have already started your video. We're going to add your video onto our gallery. Come up to that camera and tell us your name and ask your question. And it looks like you need to unmute.
When will IXPE launch? And I am Kira from the Crest Academy.
Fantastic. So Sarah, let's have you answer that question. When will IXPE launch? Thank you, Crest Academy, for that question.
Yeah, good question. So IXPE is going to launch later this year. Early December is one of the target dates. It's going to launch out of the Kennedy Space Flight Center in Florida. And I encourage all of you to keep track of the NASA feed because it will be shown live on NASA TV. It's a night launch, so you're going to have to stay up past your bedtime.
Oh, darn. That sounds just terrible, staying up a little bit too late to watch a launch. Fantastic. Stephen, anything you want to add to that one?
No, I don't think so. You got it.
All right. So hopefully looking at a December launch. That's great. Let's grab one question from another group from Crest Academy's Miss Bass O'Brien's group. So we're going to bring your spotlight in. Go ahead and unmute. Tell us your name and ask your question.
My name is Ryas, and my question is, how long will it stay in space?
Awesome. Stephen, let's have you answer that one since Sarah took the last one. How long will IXPE
Sure.
stay in space?
I believe the baseline mission is 2 years, and that's where we've already planned out all the things that IXPE is going to look at. After that, there'll be a period where people can propose, and a committee will decide what IXPE looks at. But as far as how long it stays in space, there's a continual process where the group of people that run IXPE will have to tell NASA how useful it is and all the great things that it's being used for, and NASA will decide to either keep on funding it or to not fund it. That's how all observatories work.
I was just going to sort of add that in as a potential follow-up question. Is there are a lot of missions out there that kind of had a planned short duration that seem to have stretched on longer. Some of the Mars rovers are some that come to mind. Is that pretty typical for missions to outlive their expected lifespan?
Oh, sure. Yeah, there's always a sort of a minimum planned phase of the mission, and after that, it's all gravy. It's all extra.
Very cool. We talked in a previous session about how sometimes scientists need to say pretty please to NASA to see if we might point your observatory in the direction that would help them out. So very cool.
That's a good point. So it actually takes a lot of effort. It takes a lot of people's work to keep an observatory going. People concentrate on the money that it takes to buy the parts to make IXPE or to build the thing, but it also takes a lot of effort, a lot of hard work, a lot of smart people to run the observatory and keep it going and keep it producing science.
Very good. Yeah, one, I think, common theme and important thing to call out here is that what we often pay attention to when there's a mission is just the drama around getting it launched and into space, right? Like those few minutes of something launching and actually reaching orbit or going to a destination. Often what a lot of people think of when they think about space exploration, but there is so much work that goes into getting ready for that time. And then after it's happened, doing not only interpretation with the initial data, but keeping things running, making sure things aren't broken, things are operational. So definitely ask us some questions about that too. You've got two very smart people who know a lot about kind of either side of that launch. Let's grab one question from Advanced Technology Academy in Dearborn, Michigan. So we're going to add your video feed in. Go ahead and unmute, ask your question, and tell us your name.
I'm Baby Bright, and I wanted to know, how do stars die and how are they born?
Oh, good question. So it seems like you're thinking a little bit about some of the objects that IXPE will study. How do stars die? How are they born? Sarah, Stephen, which one of you would like to take that?
I can take a stab at it.
Okay, and Sarah, you can follow up with some more info afterward. I know it's a complex subject.
So yeah, there's a lot going on there. So stars are generally born when mass collapses and becomes more dense. And as it collapses, it heats up. And if there's enough matter there, it heats up to the point where that matter can start to undergo fusion. And it's kind of like burning, but it's not burning. Burning is a chemical process. Fusion is a nuclear process where you're changing elements into other elements and energy gets produced as a result. But that's the basic idea, is that you start out with one element and there's a nuclear reaction that happens and you get a lot of energy released, and and that's what fuels the star. So the star is trying to collapse on itself. Its enormous mass is pushing down, and this nuclear fire at its center is pushing back up. It's a balance. The way a star looks is a balance between these two forces. And when the star's fuel is depleted, different things can happen depending on its mass. It can either puff up into a red giant star and have sort of a quiet death, or it could have an explosive death. If it's massive enough, it can die in a supernova explosion and produce possibly a black hole or a neutron star. We call those compact objects. So those things, the fate of a star depends on its initial mass and what it started out being made from. Astronomers call it the metallicity, the portion of elements that are not helium and hydrogen in the beginning of the star.
Interesting. So a star's ultimate fate kind of depends on its beginning. Sarah,
right.
To turn it over to you, because I know you are also an astronomer by trade. You've got a whole wealth of space knowledge for us. I think a lot of questions that come up kind of after that question is like, what will happen to our sun? Some people ask, is our sun going to be a black hole? What happens after that? So could you tell us a little bit about that?
Yeah, that's a great lead-in. I was going to talk about how boring our sun is, actually. Yeah, so our sun is kind of in the middle of the range of all the different kinds of stars that the galaxy can make. And our sun's going to live a long time, about twice as long as it's lived so far. And when it depletes its fuel, as Stephen indicated, it will puff up. It'll puff up maybe 2 or 3 times bigger than it is. And then it sort of just has a puff, and it lets off these outer layers, and it will become a little sort of remnant of a star. It's called a planetary nebula in the middle. And it's a little white dwarf that will just sort of cool off and fade away into the blackness, into the universe. And so it's a non-explosive event. It's not very exciting. It's kind of boring. But what I wanted to say too is that because we only have our sun to really study in great detail, it's really important for astronomers to have access to the different wavelengths and the different kinds of observatories that have different spatial resolution, or taking spectra of all of the objects in the heavens, to really be able to understand the physics in these other environments, because they are just not near us. All we have is our one boring old sun and our other planets in our solar system. And so if we want to learn about anywhere else in the universe, we really have to just take observations, because we cannot go there. They are simply too far away. And one of the other things I wanted to point out is, for time immemorial, we've been looking up at the heavens and seeing the pinpricks of stars. And what we see in those is the visual part of the electromagnetic spectrum. And that's the part that gets through our atmosphere, which we love our atmosphere, right? But X-rays do not penetrate our atmosphere. So we cannot do X-ray astronomy from the ground. We have to go to space in some way and get up above the atmosphere of the Earth. And that's one of the really crucial, impactful things that IXPE will be able to do, because we just have no access to those photons from the ground.
I think that's a really important point, and something I definitely want to call out. We had a student ask us in an earlier session today, why do we study space? Why are we doing this? Which is a good philosophical question to start your day with. And I think that's an important detail to sort of call out as we think about that question, right? Is there are only so many things about our universe that we can study here on Earth. We cannot create these extreme conditions in a laboratory as much as we might want to, as cool as that might be. Our atmosphere blocks out a lot of these things from actually reaching the Earth, so we have to go outside of it to learn about all of these things. So thank you for pointing that out. We have some questions in the chat that I would love to have you both answer before we move along, and I do see some guesses coming in for what LEO stands for, or what LEO means, so keep those coming if you haven't yet. One question comes from Eagleside Elementary School down in Fountain, Colorado, so not too far from us. They are wondering how far IXPE will travel. And I know, Sarah, you're going to tell us a little bit about that in a second. So maybe what we can answer instead is how far IXPE will look and how far IXPE can see. Stephen, would you like to take that one? How far is it going to be able to look into space?
Oh, that's a good question. We don't usually think about objects like in terms of a more powerful object can see, and more powerful helps can see further. I think they'll be mostly galactic objects. I think that's the answer I can give.
And so that means
although
within
we will
our
be
galaxy.
looking, that's true, we will be looking at AGN, which are extragalactic objects. That means outside of our own galaxy. So we'll be looking at objects that are very far away. One thing to note is that if you look at an object that's extremely far away, it has to be brighter. It has to be bright enough to see. So a black hole in our galaxy, we wouldn't be able to see that kind of object if it was at a galactic distance. We can only see extremely bright objects at very far distances.
Very cool. So if something is kind of dim, we might not be able to see it. Or maybe someday there will be an even more powerful telescope that can pick it up. But for the IXPE mission, things need to be really bright if they're going to be really far. Fantastic. Let's pull just a couple more before we move on. Let's see. Here's one that this is a question I never knew that I had until it was asked. This question comes from Carlos, wondering if we name black holes. So we obviously name things like planets. A lot of stars have names. A lot of features in our universe have names. Do black holes have names? Sarah, do you want to take that one?
I'll just answer very briefly, but Stephen's probably much more qualified to answer this since this is what he studies. But yes, I will say the short answer is almost every astrophysical object has a name. And it depends on the frequency, the wavelength that it was observed in, and then also how it was discovered. If it was a transitory thing, it might be in one catalog, versus if it was an optical fuzzy source, it's going to be in a different catalog. but astronomers love to name things, and so most objects in the sky have multiple names. But Stephen, I'll leave it to you to describe how black holes are named.
Sure, I think that's a great point. So I got two off the top of my head. So I think the first black hole that was definitively called a black hole it's called SIG X1, Cygnus X1. So it's in the constellation Cygnus, and it's the first object of this type. And so that's how they came up with that name. But what Sarah was getting at was that when you observe, what the point I wanted to make was that when you observe objects with a telescope, we call them sources. We don't necessarily know what they are. It's just a bright spot in an image that a telescope found. And you study the source, and maybe you can figure out what it is. But in the beginning, it just has a source name. So one that I know off the top of my head is HESS J0632 plus 057. And that was discovered by, it's an object that I studied. I wrote a paper on it a while ago. And it was discovered by the HESS telescope. And those numbers are the coordinates in the sky for that source.
So it's a little bit about just where it was found, what are its characteristics. There's almost like a code that you all can use to kind of keep track of some of the characteristics.
There are many different codes, many conventions. So that particular convention is just that the HESS telescope names their sources by the coordinates.
Very good. Can we just call out for a second two really awesome things that you just said, which first of all, you just have that code and those coordinates memorized. I don't think I could ever do that. And you just casually said, oh yeah, I discovered this object. I wrote a paper on it. It's no big deal. So just needed to call that out. All right, let's grab, I think, one more from the chat and then we'll move on. We've got some exciting things to share with you. Oh, I had a good one and I lost it. Oh, here's a good one. And I would love to know, one of you can claim this one maybe depending on whose expertise it fits in with better. A question from Richard wondering, how does IXPE avoid space debris? I know that's kind of one challenge that often faces scientists as we're working on putting things into space. How do you make sure it doesn't run into anything, whether that's another satellite or something a little bit further out? So which one of you would like to take that one?
Sarah, do you want to take that one?
Yeah, I'll have a go at it. Yeah, so IXPE is going to be in an orbit, which I'll talk about in a little bit. It's very well known. Like all of the other folks in the world who keep track of satellites will know just where it is. So chances are pretty good that it's going to survive and won't be hit by something unknown that's large. So there's a committee at the international level that sort of keeps track of all the different orbits and who's in what orbit at what time, so that the orbital planes don't get too crowded. And so IXPE will be in one of those planes. That's for large stuff. For small stuff, there's really no avoiding it. And so that white blanket on IXPE back there is this MLI, this multi-layer insulation. And it's just like a blanket you might use to cuddle with in bed, except that it's specifically stitched to have little separators that keep the different layers of the blanket separated. And it's many, many layers. And so if a micrometeoroid or some other small space debris hits IXPE, it will penetrate through some of that, but hopefully not all of the blanket, as the blanket stanchions slow it down. Now, if a particle or a loose screw or something hits one of those solar panels you see in the picture now, it will probably knock out a small chunk of the solar panel. But IXPE has been over-designed so that we can handle the space debris that we anticipate in the orbit that IXPE is going to. So we know sort of how much extra stuff is up there at what size scales. And we've built IXPE, we've designed it to kind of succeed in that orbit, to survive.
It sounds like there's a certain amount of this kind of stuff that you just can't avoid and you just have to plan for it. Kind of like
it's getting very crowded up there.
Yeah, yeah, there's a lot going on up in space these days. Awesome. Well, I think that is all the time we have for questions at this moment. We can come back for some more questions later. I do notice that a lot of questions in the chat right now are questions like, how is IXPE going to launch? What's the best way to launch a rocket? There are a lot of questions kind of centering around this theme of launching and what's going to happen to IXPE next. And you're all in luck because that's exactly what Sarah is here to talk about next. So we're going to take Stephen's video feed off of the screen for just a quick moment. He'll be back in a little bit to answer some more questions. I'm also going to disappear in just a second, but we're going to turn it over to Sarah to talk about the answer to some of those questions. We do also have, I'll read out real fast, we have some answers to your question of what Leo stands for or what Leo means. Let me see if I can find some of them. There's a lot going on in the chat today. Lunar Expedition 1 is a good guess. I do see a couple of guesses, a strong association with that constellation Leo, which good call on picking that up. Yeah, Lunar Expedition 1, low energy orbit, and I think I see one correct guess. So we'll let you reveal that one so that this person can feel very proud of themselves.
All right, thanks, Talia. So LEO, L-E-O, stands for low Earth orbit. So if you wrote that in the chat, give yourself a pat on the back. Good job, you know your space. IXPE will be headed to a low Earth orbit, which is around about a couple hundred miles above the surface of the Earth. And as we talked about earlier, I think IXPE is going to launch in December, early December. It's going to launch out of Florida at the Kennedy Space Center down there on a Falcon. I think it's a Falcon 9. Everyone's nodding. Yes, Falcon 9 launch vehicle, which is a massive rocket. And IXPE, right here behind me, right, that's the real hardware, is tiny. It's like my size, maybe a little fatter than me. And it will be this tiny, tiny little thing on top of tens of stories of rockets. And so all of this planning has been going on for years to procure the launch, to get IXPE tested for launch, and we're going to ship the thing down here very soon, so it goes to get integrated onto the launch vehicle, and little tiny IXPE will get lifted way up on top to be put on top of the rocket. Once it's countdown time, right, we all count down from 10. Once we hit 0, off goes the rocket. It takes very, very little time to get through the atmosphere and up into space. And the rocket will put us on a particular trajectory to get IXPE into a low inclination orbit. So let me pause and tell you a little about some of the low Earth orbits that we have access to. So if this paw is the Earth, and this is the spacecraft, you could imagine going around the Earth's poles in an orbit, in low Earth orbit. And if you go over the North Pole and then you go over the South Pole, that's called low Earth orbit and a polar orbit. For IXPE, we're actually doing 90 degrees from that. If this is my Earth, and here's my little satellite going around my hand, around the Earth, we're going to go around the ecliptic, around the equator of the Earth. And so this is a low inclination orbit. This is particularly important for IXPE because the detectors that will pick up those really sensitive X-rays are very sensitive. The detectors are very sensitive to any kind of high energy particles that might impact them. And the Earth's magnetic fields produce and constrain a lot of these high energy particles that come from the sun and come from outer space. And so we want to be in a place in that magnetic field that has low flux of those kind of high energy particles. And an equatorial low inclination orbit will do that for IXPE. Other science missions are designed particularly to use polar orbits or slightly inclined orbits of varying sizes. Low Earth orbit has around about a 90-minute time period. So IXPE will be on the sunny side of the Earth for 45 minutes and then on the back side. And it will just go around about 15 times a day, taking data when it's on the dark side, collecting solar power, downlinking data when it's on the sunny side. And it will just do this as we go around the sun in a 2-year period. IXPE will have completed its primary mission, collected all the data that the science team so far knows it wants to collect, and then hopefully head into an extended mission. So I do want to pause and say that slightly after orbit, we'll get on orbit, we'll be in this low inclination orbit around the equator. We'll send a special command after letting the observatory sort of outgas for a little while. We'll send a special command that will pop open the boom. And I want to highlight that you can all build an IXPE with its extended boom. It will look like this when it's complete. And you have information for this kind of model in the chat. If you build it out of the right material, something sort of stiff, you can actually get your boom to swirl down and collapse and then pop back up. It's kind of cool. This is exactly the observatory that you're seeing next to me. That's the same creature. So pretty cool.
That is super cool. And we will email those instructions to you if they have not already arrived in your inbox. So those will come via email. All right.
I think I'll stop there and see if there's any other questions. Yeah.
All right. Super interesting stuff. Always cool to think about what happens next. And one of the things that I was kind of thinking of as you were describing orbits is they almost kind of sound like highways. Like So I live in Denver, where we have I-25 that runs north and south, and I-70 that runs east and west, and a few other smaller highways that kind of go around and connect some of those. And wherever you live, you might have highways or particular roadways that create sort of paths that you make through your city. And it sounds like that's kind of what orbits are, right? Is they're like highways that go around the Earth. Super cool. So you don't just launch something into space and leave it.
That's right. Yes, you want it to go where it will be most useful.
Perfect. Let's grab, we have, maybe 4, maybe 5 minutes left in our program. Let's grab a few more questions from the chat. So if you have not put one there yet, now is the time to do it. We've had a lot of questions in the chat, so no promises that we will be able to answer every single question today, but we will certainly try our best, and maybe we'll go a little bit rapid fire. So I'm going to bring Dr. Bongiorno back on the screen, and let's see what we can do. Quick question for you, Sarah. How heavy is IXPE?
That's a really good question. Yeah, I haven't talked about that today. It's pretty heavy. I mean, it's heavier than me, right? I don't have the number off the top of my head. Does anybody know? I'm looking at my team here. It's hundreds of kilograms.
Hundreds of kilograms.
Even
okay.
Do you happen to know?
No, sorry, I don't know off the top of my head.
That sounds like a fabulous question for the Google machine that our students can use just a little bit later. That's something that you all can look up. Awesome, fabulous question. One question that I've seen pop up multiple times and that Stephen has answered in the chat, but that I do want to call out again, is are there any people going up with IXPE? You want to tell us about that one, Stephen?
Sure. Yeah, no, so IXPE is not designed to work with astronauts. It actually doesn't need anybody up there to physically touch it and say push buttons or plug things in. It's designed to work by itself with no people there. So people are needed on the ground though. So there's a team of people that will be on the ground that send radio signals to IXPE. We call them commands to tell it what to do. And so there are computers on board that take those commands and they will steer the observatory to look at different objects.
Awesome. Yeah, I think that's an important thing to call out. I think a lot of people, again, associate space exploration and space missions of any kind with needing an astronaut, and that's not in fact what happens. We need lots of people. So maybe you're someone who likes playing video games. That's a skill that could potentially transfer, is the ability to know what's going on and use your hands and use your mind to make something happen that you're not able to touch. Pretty cool. Awesome. Here's a question coming from Zoe. Zoe wonders, does IXPE stay in one particular orbit or could it be steered? Like if you needed to move it to a different orbit, is that something that can happen? Sarah, could you take that one? Is that a good one for you to answer?
Yeah, absolutely. So IXPE we're planning to keep it in its equatorial orbit for its whole life, but it is absolutely steerable. So while it's on the dark side, on the nighttime side of the Earth, it will point to all of the objects that Stephen and his science team want to look at. And so as the observatory goes around the sun with the Earth, we'll collect data on all of the dark sides, right? Which will collect the whole of the nighttime sky. So whilst it's not pointable, it's not maneuverable into different orbits, we can absolutely change where it's pointing, north or south or in the ecliptic, to look at different kinds of objects.
Probably pretty handy for Stephen and the science team if there's something new that you want to study. Awesome. We have about 1 minute left in our program, and I'm going to call out a question that I saw come in the chat only a few minutes ago. We kind of touched on it a little bit earlier, and I'd love to hear your thoughts on both of it, or thoughts from both of you on this question. Why do we need to know about space? Maybe we can tie this into a little bit of a wrap up of why is it important to you that we study space and learn about our universe? And if there's someone else watching today who's interested in learning more about space, what would you recommend to them? Sarah, let's start with you.
Why is it important to study space? Well, I think we're all just curious creatures. So we want to know what's out there. We want to know how the universe works. We kind of want to know where we came from, and we kind of want to know where we're all going. And also, sort of subsidiarily, we'd love to know, are we the only creatures in the universe like us? And so studying astronomy, building hardware like IXPE gives us access to answers to all of those questions. And as a sort of aside, we need people of all different types to do this kind of work. We need scientists like Stephen. We need engineers who place astronomers like myself. We need business people to keep track of the money for how to buy things, how to spend money. And we also need folks who can communicate, folks who are good with their hands to put things together. It takes a huge amount of people to do this kind of work. So if you're excited about this, I encourage you to find an outlet that you are excited about and be really, really good at it. And then you will do well in your career.
Awesome.
Over to you,
Fabulous
Stephen.
advice. Yeah,
I think
Stephen,
that's a great point. That it's not just scientists and engineers that get to work on space stuff. There's a whole lot of different people, like you were saying, Sarah, that get to work in the space industry. So that's good. That's a good point to keep. If you want to work in space, you can keep your ear out. You don't just have to be a scientist or an engineer. So I wanted to add one other point to that. So yeah, I think that's really important to talk about sort of the philosophical curiosity and to say what's going on out there. You know, how does the universe work? Where is it going? Where did we come from? But something else I want to bring up is that these are physics laboratories, these objects that we're staring at, and we can't create those conditions here on Earth. So we can actually learn more about physics. And when we know more about physics, that always trickles down to engineering and the technology that we get to use in everyday life. So it's always good to learn more about physics. That helps our everyday lives.
Fabulous. And what advice would you give to someone who's interested in a career like yours?
Oh, learn to code.
That is a good piece of advice. That's a growing skill set, or a skill set that's becoming increasingly useful. So something for anyone who's maybe thinking some thoughts about what they want to do when they grow up, keep in mind. All right, that is about the time that we have today. So I do just want to say a huge thank you to Dr. Sarah Lipsey from Ball and Dr. Stephen Bongiorno from NASA for talking to us about this incredible mission. I'm super excited to learn a little bit more about IXPE as the mission progresses, as we launch, hopefully in December, and as IXPE continues to, or starts to return data to Earth about some of these mysterious objects in space. I learned a lot today, and I hope that all of our students did too. So students, thank you for your insightful questions. Your great observations. We always appreciate getting to learn and hear what you're excited about today. And we challenge you to go out and learn a little bit more. Keep following along with IXPE. Watch that launch when it happens in December, and continue to learn and explore and get curious, get excited about space. We hope that you'll join us for other exciting virtual experiences happening through the rest of the school year. And if you're one of our on-camera schools as we leave today, feel free to unmute and say goodbye. Thanks for being here, everybody. Stay curious, and we'll see you next time. Bye, everybody.